Hi guys, today we are going to do a recording on energy for your IGCSE Form 4. It's on chemical energetics. And the first thing, of course, we talk about energy. So in this case here, energetics of a reaction, chemical reaction. Energy means change. Basically here we talk about heat energy. Okay, and of course, how to measure heat energy? By temperature. Okay, increase or decrease of temperature. So in the core, it says the meaning of exothermic. Exothermic means the heat is given out. Heat is given out. Okay, that means temperature will increase. Okay, right? From 25 degrees centigrade go to maybe 40 degrees centigrade. Okay, endothermic means heat is absorbed. Heat is absorbed. Okay, it can have two. One, of course, the thing become cooler, colder or cooler. The temperature will drop. Or is just absorb heat, absorb heat from a Bunsen burner. From burner. Also, you can say that it is endothermic. Okay, so must interpret with energy level diagrams. Okay, I'll show you what it means. Both of these reactions, exothermic and endothermic reaction. Okay, now let's go to supplement first before I go into the notes. Describe bond breaking. See, you break the bond here. Basically, here we talk about is covalent bond. Like for example, when you form a bond, let's say for example H dot plus Cl. Remember? Okay, this form your HCl dot cross. Now, when you form the bond here, these are stable. Why? Octet, isn't it? 8 octet and then duplet, isn't it? So it's stable. So this is unstable. So from unstable to stable, that means that it will be more stable. That means in this case here, right? This is stable. So when it's stable, heat is given up. Okay. So when bonds are formed, right? So it's plus stable, heat is given out. That means exothermic. Okay. Stable means heat is given out. When bonds are broken, let's say I'll break this bond. Okay, put blue color. Okay, I break this bond. That means I must have heat to break the stability to go backwards. So when you break the bond, right, it's endothermic. Okay, because you break something stable. Okay, again you need to draw the energy level for both of them, right, and calculate the reaction. So we're going to do all this and others later. I'll show you first. Okay. So, but I will do more other kind of reactions as you've done in the class. Okay, and the first thing, of course, here you have the definition. Okay, when chemical reaction occurs, bonds or reagents are first broken. To break the bond, of course, because the bonds are stable, you absorb energy. So it's endothermic. Like here, right now, this hydrogen, H-H. To break this bond, I require energy. Okay, so now here you can see they give the bond energy which you need to use to calculate. HH bond, see now, here's one here. HH bond is 436. That means you break this bond, HH bond, you break it. Because it's stable, duplet, isn't it? Yeah, duplet. Stable, isn't it? So break it from H dot and your H cross. So to break this bond, I require, that means positive 436 kilojoules. Okay? If I form the bond, go back here, it will give up. It will release, it becomes stable, minus 436. Yeah. So break the bond is endothermic. Form the bond is exothermic. Okay? Right? So that's quite simple, isn't it? So you must remember that. Okay? Right. Now, so here, now there are a few reactions which you have done in the class. The first one is, remember, here, I asked you to add ammonium chloride to water, right? Okay, when you put ammonium chloride 2 spatulas into boiling styrene, can take the initial temperature and the final temperature, you find it become cold, isn't it? So it become cold. Why? Because it's absorbing heat. So it become cold, right? From here to here, temperature drops. Okay, become cold, right? So cold means that energy, right? Energy is absorbed from the surroundings. From where? From the solution. So temperature drops, feel cold, right? So to break the bonds, you absorb the heat. So now how do you draw the energy diagram? Now here is it. Okay, I'm going to use grid here. So I've drawn it so that it gets easier and faster for us. Okay, so the energy level here, right? Reaction pathway here. Now this is where your reagents are. Your ammonium chloride plus aqueous. Before reaction, after reaction, you go up here. And then it goes up here is endothermic. This is positive. Okay, going up is positive. Going down is negative. Right? So it's endothermic. You must say endothermic and showing here. So this is the energy level diagram. This, of course, is your copper sulfate. Remember, you did it here. Copper sulfate. Or copper nitrate is the same. Copper sulfate, I think, yeah, here. Right? Remember? So you put a test tube of copper sulfate. Blue means hydrated. Okay? Got water crystallization. And you heat until all the water crystals have come out. So your system here is absorbing heat. Absorbing heat. That means also is what? Endothermic. No, absorb heat. Okay? To form this one here. To form your white, it will ask you to color. White anhydrous is called white anhydrous copper sulfate. Okay? Now I'm telling you, if you cool it, cool it and wait for it, okay, to touch cool enough. You put some water inside, it means it will go backwards. And you could touch it, it's very hot, isn't it? So going backwards, right? The bonds are formed again. Going backwards is exothermic. Going forward is endothermic. This is called a reversible reaction, which you will do later in the next session. Reversible reaction. Okay? Okay? So you can see depends on up or down. Now this is the energy level diagram. You see that? I put blue color. Okay? This is the energy, this is the y-axis is energy. This is the reaction pathway or axis. So where to put the anhydrous and where to put the hydrated. Okay, depends on where I start first. I'll start with your hydrated, the blue color one. Okay, I put copper sulfate plus 5 water solid here. So to go upwards, to go you give you anhydrous. This is a white color. This is anhydrous, anhydrous. Okay, so go up here. Is absorb heat, right? Endothermic, give water here. So if I like cool and I add this to here, it will come down. Okay, it's exothermic. So you can see if you start with this, you go up here. You start with this, you're in down here. Okay, so remember, they want the energy level diagram and the reaction, exothermic or endothermic. All right, next one here. Okay, now this is, now I want to show you how to calculate, okay, because they ask here, remember, right, calculate, see, calculate the energy of a reaction using bond energies, okay. So bond energies normally here refers to covalent bonds only, covalent bonds, okay. You do this in Form 6 as well, covalent bonds, okay. So now let's look at some examples here. I'll give some examples here, then we'll do a passive questions, okay? So now the first example, of course, is combustion of water, right? Water here, right? Water. Water, when you burn hydrogen in oxygen. So hydrogen has got H and H bond. So two of them will burn with oxygen, it's got double bond. You must know, no? To give you, now what bonds are formed, water is oxygen here. This is all you've done before, right? So two of them, okay? So in this case here, from here, these are your reagents or reactants, which must break the bonds. So I put blue color here. So I must break this bond. I must break this bond, okay? And then I must form this bond and form this bond. So reactants is to break bonds. You must break the bonds. In your products, more bonds are formed. Covalent bonds are formed. Okay, covalent bonds are formed. Okay. Okay. When bonds are formed, is exothermic. What's more stable? What? When you break the bonds, is endothermic. Okay, you require energy to break something. Okay, this is positive. Right? So how do you find the overall heat change, or I call it the enthalpy change? It's called the heat change, or they call it the enthalpy change. Enthalpy change. Okay, so two words of it. Enthalpy is a very big word, but it just means H. Okay, so you first of all do it by a very simple method called bonds broken and then bonds formed. This is the same method they use in marking sim. I will show you after. Maybe I show you here. See, right? Bonds, mark it, huh? See, red color. See, bonds breaking or bonds broken, bonds formed. Okay, and then here's the overall reaction. See, they do this like this. So marking sim, we do it marking sim method. Okay, so now here. So now remember here, I need to break bonds up. So you can draw it out there. Okay, now here, put here, bonds broken. Sorry. Okay, here, I put up here, sorry. All right, the one is carbon dioxide. Okay, hydrogen here, bonds broken. I put red color, so you can see a difference. No, it's not. Okay, see, bonds broken. So how many bonds are broken in this water here? In a combustion of hydrogen to form water? H bond. How many H bonds are broken? Because there are two molecules, so it's 2 times HH. If it's one molecule, it's just a H and a H. If it's 2, I must times 2. So 2 times 1 bond broken. Now remember, 1 bond broken, how much is it? Look at here. They will give it to you. Now here, I've got the whole chart here. So for one covalent bond broken, 1 bond is 4, 3, 6. It means broken, it means I must positive. Absorb heat. Okay, so here is positive. See? Right? So 2 times positive 436 is 1 bond broken. Okay, now for oxygen O2 here, O and O only 1 bond. This is 1 O bond, O double bond O. So I look here, the O double bond O is how much heat is it? This one here. They don't put a sign there, it means positive also. Okay, 498. So for 1 double bond, O and O is 498. So here I put here 498. See, 1 times 1 means 1 only, not 498. Right? So the total I add up here is plus is the total heat required is endothermic. 1370, I calculated kilojoules per mole. Now bonds formed. See, for 1 mole of water, okay, 1 mole here, how many OH, the bonds are OH bonds in it. So how many bonds are there? 2 in it. So I got 2 moles. So 2 times this, or I can say 4 OH bonds are formed. It's not. So here, so 1 OH bonds, how much is the bond energy? Check again here, OH. OH, where's OH? OH, here we are, OH. 464. So 464, I put down here, right? So 2 times 2, 4, okay? So put 2 here first, okay? Just in case you don't understand, okay? So this is the one. So the total is minus, why minus? Bonds are formed. Exothermic, isn't it? 1, 8, 5, 6. Okay, so plus here. So now this is the equation, this is a formula. So heat change, this is your heat change, okay? Heat change. Okay, or enthalpy change. Or overall change. Enthalpy change. Or they call it overall heat change. They don't use so bombastic word. Heat change. Is equals to, now this is quite simple. See, it actually means I put down here, okay? Bonds, bracket, broken, plus bonds formed. This you will see you use in Form 6 as well. Okay, so now the sign is very important. So a bracket, okay, the sign here you know is positive, so you put positive here, okay? So it's positive 1370 plus. Now here, because bonds are broken, is negative now, okay? A form is it, negative is it, right? Put a negative here. So the overall is minus. So minus 4 means this negative means is exothermic. Okay, you must put down the value and ensure it's exothermic. Okay, that's why you burn hydrogen, you get a lot of heat, isn't it? Right? A lot of heat, energy, right? energy to run your batteries, all these things. Now another question, of course, is here. So I'll give you another question here. Okay, right now, combustion of fuels, combustion of carbon. You burn carbon and oxygen. Here, carbon dioxide, isn't it? Yeah, carbon dioxide here. So what is the heat change? Now, carbon is element, so the bonds, we're going to put 0. Okay, 0. So for element, if it's 1 here, sulfur or whatever, if there's nothing here, just carbon here is 0. Okay, so here I'm breaking this double oxygen, double bond oxygen. So it's one of them. So one times this, right? 498. Why 498? That carbon double bond carbon on top here. Sorry. See, 498. Okay, now oxygen double bond carbon, oxygen double bond oxygen. Okay, so here's 498. Okay, right. So the total, of course, is still 498. Positive 498, because carbon here is 0, isn't it? Remember, elements, nothing to break. Okay, so now for this carbon dioxide, remember this is the formula. So how many, what kind of bonds are there? Carbon double bond carbon. Oh, how many are there for one molecule? 2. So 2 times 1 type of C double bond O. So what is C double bond O? Can here. They will have to give you this value now. Okay, 805. Okay, 805. So 2 times 805. This is the value. So again, then they use the formula here. Heat change equals the bonds broken first plus bonds formed. The sign important, because it's bonds formed is negative, isn't it? So you must put the sign here. So this one plus 498 plus minus 1 here, you minus off, you get minus 1112 kilojoules per mole. The unit is also important. Okay, right? So the other one, of course, is the famous one. Come for a lot of exams on. Okay, burning of methane. Okay, methane. Okay, methane. Now, methane, of course, I know that it's not organic chemistry, but you must know methane is a gas you use to light a fire, you know, in the house of sharing gas. Okay, methane. Okay, CH4. So now there are 4 CH bonds here. You need to know. Okay, they draw the molecule for you. Why not? 4 plus oxygen. This is a balance equation. 1 mole requires 2 moles. To give you 1 mole and 2 moles, you must know how to balance the equation as well. Okay, we've done before. So bonds broken. You have this one and this one here. So for methane is what are bonds there? CH bonds. How many are there? For one molecule? 1, 2, 3, 4. Why not? So 4 CH bonds. So 1 CH bond is what's the value? You can see here CH bond, 413. Yeah, 413. So here be 4 times 13 is plus 1652. Okay. So what else is broken? Oxygen. 1 mole is 102. So 2 moles. So 2 times this, again, O and O is 498. You can see again, O and O 498. So you put down here, right? 498. 4 times this, so 996. Okay, positive, why positive? Endothermic. So add up is plus 2648. Okay. So now bonds are formed. There's carbon dioxide and your water. So for 1 mole of carbon dioxide, got 2 CO bonds. So I put 2 here. Again, you can check this value out. For water, 1 more water got 2 OH bonds. So the 2 here, I put 4. Okay, you can check out. So the total is on here. So again, formula, heat of reaction, bonds broken plus bonds formed. So you can see here is negative. You must say so exothermic. Okay, now. Okay. Okay, is it? All right. So easier. Now, so now I want to and now energy levels here. All right. So remember, one energy is a methane here, methane in your oxygen here. Because overall is exothermic. What? See now, negative, isn't it? Negative. Right. So you must put the products down here. Carbon dioxide and water. So it's down here. So normally they will put a graph going up like that. Later you see, right? And this is called the activation energy. It's called the EA, or it's called the activation energy. That means you must have this energy for it to break. It's like you must like a match, isn't it? to burn the labo gas, right? You must have a flame. You go to the lab, you on the labo gas, you must light a flame, then it burns. Otherwise cannot. This is called the activation energy. The energy provided to start the reaction, activation energy. Okay? So you learn a few things today, right now? Okay? Now, the other one, of course, is then to calculate further. Okay, now here is for this thing which some of you did. Neutralization is here, right? Neutralization. Where is it? Okay, here. Acid and base reaction. Okay, right? You will find that initial temperature, maybe room temperature, and you find that here will rise the temperature maybe 35 or whatever lah. Okay, so again, it's exothermic lah because temperature rises. Okay, so we're going to see how we can calculate this one here. Right, now put down here, always remember start with the equation, this equation. Remember, it's a neutralization reaction between acid and alkali or base. Right? Now, I put the equation here, HCl equals, NaOH equals, first give you 1 mole and 1 mole. The key word is water actually. So 1 mole, with 1 mole, give you 1 mole water, okay? Right? Now, to do all this calculation, there are 2 parts here. I put the blue color so you can differentiate it. First, of course, is to find the number of moles, number 1. Find the number of moles, mainly of water. Secondly, here, number 2, to find the heat change. How much heat is given up during the reaction? Yeah. So there are 2 parts. So that for number of moles, the first thing I need to find is how many moles of HCl do I use? How many moles of NaOH do I use? Okay. So I use number of moles equals to mV or 1000. Remember not? So M, of course, is your molarity given here. V is your volume, 50 over 1000. So the number of moles of HCl we should use is how much? 0.05 moles. Right? And the number of moles of your NaOH, same thing here. Number of moles of NaOH is equals to mV of 1000. M, of course, is 1 times this here is also 0. So its number of moles of NaOH is same. So they both are ngam, they both no excess in it, right? If this is 0.10, that means that this will be in excess, right? This is the limiting factor. We done before already, okay? So if this is 0.05, that means how many moles of water? Also 0.05. Because why? 1 mole, right? 1 mole give you 1 mole, okay? So here also is 0.05 moles of water form. This is very important. From here we calculate, okay? 5 here. So 0.05. So then we go to here, okay? Heat change. Now this is the thing which I think you learn in physics, okay? Heat is equal to mc theta. M means the mass of the whole solution, which is here 50 plus 50. You think the volume is actually equal to mass because density equals to 1 gram per dm cube. 1 gram per cent. Now, okay, just remember the volume is 50 and 50 means 100. That means you put here as 100. This is the mass. Okay, mass of the whole solution. C, of course, is 4.2. It's a specific heat change. Okay, and this theta is a heat change. The temperature is initial is 25. Final is 31.5. So you minus that is 6.5. This is the difference, temperature difference. Okay, so you put here. So theta is the temperature difference. You times it out. It's minus 2730. Why minus? Because temperature rise from here to here. Increase in temperature is exothermic. So from here, we conclusion. Okay. So 0.05 moles of water is H2O here. Form, right now, this amount of heat is given out. See now, this amount of water gives this amount of heat. Minus 2730 joules, joules. So for 1 mole of water, will be this or this times this, which is in joules and is 54.6. Now this is experimental value. Actually, theoretical value is minus 57.3, which is accurate. But now it's quite near zero. Okay. So now this is called the heat of what? This is called the heat of neutralization. For per mole of what? Per mole of water form. So I want to change this into a energy level diagram. Very simple. Same thing. Energy level here. All right. reaction pathway axis here. So because it's exothermic, I put my radian up here. Okay, or NaOH equals and equals. Okay, so going down to my salt equals plus liquid water here. So this is the heat change. Going down means what? Exothermic. Okay, right? Okay, now the last one which we talk about is of course spirit lamp. Okay, the spirit lamp, which means you burn. Look here, we burn the spirit. The lamp. We measure the amount of heat change, right? You can see in here. I actually got a, well, I hope I got it here. No, don't have. I thought I got it here. Never mind. Right? You burn the spirit lamp, okay, and then you actually like this, okay. Got the spirit lamp here. Okay. It's a wick here, and it burns it out. This is your, we use methanol. Okay, it's CH3COH, and there's a beaker or something here, and you measure the temperature. Okay, the mass of water is here, 100 cm cube of water, and temperature before and temperature after. So see, from here you calculate the heat change, MC theta. Okay, right? In fact, how much of the, after you burn, you weigh again how much of this is used, how much mass used up. Okay, so two things you use. Okay, so here let's say we have got it here. Weight of spirit lamp plus methanol is 100 grams. Okay, this before you burn the filler. Weight of spirit lamp after burning, less than that. Why? Because from here to here, the methanol has been burned, isn't it? So how much methanol is burned? Mass of methanol burned, mass of methanol burned equals to 100 minus 85, which is 15 grams. Temperature rise from 25 to 75. So first, of course, we find the delta H. How much heat is gained from the water? So MC theta, mass of water is 100, okay, because it's 100 cm cube. So it's grams at 4.2, same, and the temperature rise here. So it's minus 2100 joules. It's always in joules, okay? So change to kilojoules, I divide it by 1000. Okay, so it's 20 minus 5 plus temperature rise, exothermic. Okay, right? So in this case here, I won't change it much first. I just put this here. So remember, the methanol burn, this is one here, going down, right, exothermic. Why? Because heat is changing. Okay, so this is the pathway. Okay, so now I finished all this already. I need to go a bit fast because why? You have to do your own study, huh? Because why? I'm very slow behind. So I need to catch up with the other fellows so that you can have a test. And then your end of the term. So we done even until here calculate. Oh, no. Now the last thing, of course, here is remember we reduce energy by burning fuels, okay? Burning your CH4, your methanol, and your methane, hydrogen. Okay, we've done this too. Now, of course, uranium. I just want to talk about uranium first. Okay, it's a source of energy because uranium undergoes fission and fusion. Here, quickly, right? You just need to know this. That's all. Okay, now here, you can read all these things by yourself in your free time, right? Here. Okay, now uranium has got two isotopes, uranium-235, uranium-238. Only uranium-235 is radioactive. So uranium-235, when you shoot a neutron inside here, right, it will break up into 2 neutrons plus krypton plus and energy. So it's exothermic. So uranium will split, okay? This is called a nuclear reaction, okay? See, nuclear reaction happens when the particles, these are neutrons, are shot into the nucleus, change the mass, become unstable critical mass, break up into smaller mass with heat energy. This is called radioactive now, okay? Right? We did this before earlier, okay? So exothermic reaction. So heat is given out and absorbed by the water. The water boils, and of course, it changes to steam energy, and it will turn the turbine and cause give electricity. Okay, so here is it, right? Right. So now fuel cells, of course, hydrogen is used as a fuel cell. Okay, hydrogen, you learn later, hydrogen and oxygen can be used to make energy, electrical energy. It's called fuel cells. That's all you need to know. Fuel cells, F-U-E-L-C-E-L-L-S, okay, to make electrical energy from hydrogen, oxygen. Okay, now let me show you some. They're finished, huh? So I want to show you some of the past year questions. We got about 15 minutes more. Okay, how they are being asked. Okay, all right, now 13 here. The diagram shows a match. By striking a match on the chemical reaction takes place. Okay, the match here is phosphorus and some oxide. Okay, so when you strike a match, it burns in. It burns in. It gives out heat, isn't it? So you have heat. Why? Because it's exothermic. You know. Okay. Now, they say by they are asking for a chemical reaction, not the physical reaction. Of course, the physical reaction is that you take a match and you strike it. Okay. Right now. Okay. But now it's a chemical reaction here. So when the match burn is exothermic. Okay. Right now, exothermic. Why? Because the energy is no. The example is endothermic. Isn't it? Why? Because energy is given out. Because heat. So E is the answer. Okay. Right now, which process is not exothermic? Fossil fuel, that means petrol, or methane. Right? Decay. This is what? This is exothermic. So this is exothermic. Burning hydrogen and oxygen also exothermic. Remember, see? Only this one here. Because limestone is calcium carbonate. You need heat. Remember, we did in the first term to get calcium oxide plus carbon dioxide. So you need heat. Heat means what? You heat it, it's absorbing heat. Absorb heat means what? Means it's what? Endothermic. Okay, for this reaction to occur. This is of course called what? Thermal, who knows? Thermal decomposition, same as your nitrate. Okay, right, not external. Right, now we go into 14 and 15 here. Coal and uranium. Coal, of course, is fossil fuel, it's just carbon. Uranium, 235. Get used to the source energy. Which of them are oxidized? It means turn to carbon dioxide. Of course, this one is not. Okay, it's not, right? So uranium is not, it's oxidized. It's broken down into small pieces. So this is the one here. So B is the answer. Uranium is split into smaller elements. Okay, now this is another good question to think about. All right, when solid acts inside water, endothermic, that means absorb heat. That means what? Temperature will what? Will decrease. Okay, 5 grams of X dissolved in 1,000. Okay, put on here, draw it out here. Here's 1,000 cm cube. Okay, 5 grams, put inside here 5 grams. The temperature, right, change by drop by 10 degrees centigrade. Okay, so now which temperature will change when 5 grams drop into 50? Half of this. It's now 50, 500. Of course, the 5 grams as well. Of course, the temperature will still drop in. Right now, right? It still drop, but of course, it's over a smaller volume. So the temperature will be higher, isn't it? 2 times more, a decrease, you know, right? This is the same heat given out over a smaller volume, you know, the volume here. So you need to look at the thing carefully. Okay, decrease by 20. Okay. Elements of H2 and U235 are both used as fuels. In this process, reactions 1 and 2 oxidize. Okay. Reactions are, number 1, they are both exothermic. Okay. Who is oxidized? And what? Only hydrogen. No, because oxidized means what? Hydrogen plus O2, 2 of them becomes what? H2O. Uranium don't. Uranium becomes break to elements. Okay, and then plus heat. Okay, very simple. They ask you for uranium. Okay, let's go to now this one here. This one here. Okay, 4 samples of 4 different substances added to water. Temperatures are measured. Which substances have exothermic? That means increase in temperature. When correct, temperature decreases, not correct. Remember, if I'm cold, ethanol, you burn, of course, wrong. You burn your alcohol, the temperature will increase. Ice, right? Okay, when you put in the water, okay, what will ice do? Okay, the temperature, hold on now. Okay, of course, it's exothermic, right? the temperature will decrease, correct? But it's not exothermic, right? Or not? Right? Okay, it become cooler, isn't it? Right? You put in water, the water become cooler, means endothermic. Sodium, you put in the water, it will dance around and give lots of heat, no? Okay, remember that in your form 2 or form 3. So this is the one here. Because sodium plus water gives a lot of heat one. Okay? Right, that's something you done in class. The diagram shows crystals of copper sulfate. Water, now this is a blue color. This is hydrated. It's blue, blue hydrated copper sulfate being heated. Crystals heat, blah, blah, steam. This is H2O here. Great color change. Which two terms describe this change? Of course, heat is absorbed, that means absorb heat. What? Endothermic. Okay, absorb heat. And what happens? Dehydration, it means it becomes no water already. It means it becomes what? Becomes CuSO4 plus water. Okay, dehydration, lost water. Okay, so here, and dehydration. Okay, right. Okay, this is quite simple. The following elements have radioactive isotopes. Which element is used? They all have radioactive isotopes. Okay, which element is used as F4Energy? Of course, uranium. Okay, so here again, this simple thing again always come out. When hydrated copper 2 sulfate is heated in apparatus shown, solid X and Y are produced. Okay, right? Of course, solids, when you heat this on here, hydrated, this is copper sulfate, 5H2O becomes that. And hydrogen, copper sulfate, okay, which is a solid X, no water, that's the water given up. This is your, and hydrogen, this is your white color, this is your blue color. Yeah, this water here, of course, is water here is what's your liquid. So, what changes notice in the P, Q, Y, and Q and solid when cold what do you notice when liquid Y is added to cold R to cold X? Of course, it turns from white back to blue, is it? Remember, it's a reversal process. Right now, white back to blue, white to blue, and heat's given out, exothermic. Right? Remember, CuSO4, 5H2O, right? Going forward, you still heat absorb. Heat is endothermic. You get you CuSO4 plus your 5H2O. This is a blue, this is your white. When you put water into this again, you go backwards here. Okay? So it's hot, exothermic. Okay? Heat is given out. Okay? White to blue heat. Okay? C answer. All right. Now I got 10 more minutes or so. I want to do calculations. Okay, 26. Just to show you the range of questions you can have. Okay, I'm sorry I cannot do this all in class because time factor is not for us. Now here, this is of course your Haber process, which you will do later as a reversible process. Okay, see here, right? Remember, this nitrogen, which is a triple bond. Okay, hydrogen here is a single bond. And ammonia here, you know, all this done before, bonding. That's not. Okay, right? So here, now we put down here, right? So complete the table, describe the bond breaking and bond forming in the reaction between nitrogen and hydrogen forming ammonia. This is ammonia, of course. Okay, so what are the bonds broken here? Now, this, of course, these are reagents, which means what? You need to break the bonds to form the ammonia. Here bonds are formed. Okay, so to break the triple bond, they give you the answer here. One bond, one mole. Yeah, one bond. So of course, positive means what? Endothermic. Look at the sign. 3 moles of H2, H, that means 1 mole is something, so 3 times 7, do it here again, is endothermic again. Why endothermic? Positive. Okay. Now they tell you it's so easy. 6 moles, 6 moles of this one here. That means 6 moles of energy. That's why. But the 3 moles of ammonia. See, 3 moles of ammonia. 1 mole ammonia got 3 bonds. 1, 2, 3. So 2 moles is 6. So they give the value here. Of course, it's exothermic. Bonds are formed. Exothermic. Using above, right? Using the above data, explain why for is exothermic. Very simple. You do the same thing as I did. Heat change is equal to bonds broken plus bonds formed. Okay, so plus 995. Okay, this is a bonds broken plus 945 plus 1138. Okay, plus now this is minus. See, they put like that. So it's minus C. Minus means exothermic. You need to show, yeah, to show why. So you do the calculation, you get the answer. Okay, now for the last one, I know 1 hour is halfway to absorb, but here same thing. Now, and exothermic reactions are produced heat change here. And important is fuel. Now, remember methane is used. Remember, you need to know methane. CH4 is a natural gas. Equation and combustion and so forth. So methane burns oxygen, give you carbon dioxide and water. Right? In the chemical reaction, bonds are broken and new bonds are formed. So bonds are broken, bonds are formed. Okay. So using this equation here, give an example. Okay. So of course, what bonds are broken? Of course, CH bonds are broken. And also you want to put here O, the one O bonds. Either one of them. Bonds are formed, right? Remember, is carbon C double O or OH bond. That's water. Okay. Now here is, they didn't ask you to calculate. They ask you to describe. Explain using the idea of bond forming and bond breaking, why this reaction is exothermic, is produce heat energy. Now remember, if the total heat change here, the total heat given out, okay, which is negative, and this is the total heat to say is total heat absorbed, positive. If this heat given out is bigger than this one here, that means the delta H will be what? Negative, isn't it? Because this is bigger one. If this side is bigger, if the heat absorbed is bigger than your heat given out, delta H is what? It is positive. So that's the best argument to give you. So how to answer this one? Right? More heat is given out because exothermic. Okay? More heat is given out when bonds are formed than heat absorbed, than total heat, then total heat absorbed for bonds to break. Understand? Okay? So these are the ones here. All right? So the isotopes and so forth. Now the last one. Okay? I've got 5 more minutes. Okay, we finish. I plan on time. We finish on time. All right? 5 minutes. Now, bond breaking is they tell you bond breaking is endothermic. Right? That means absorb energy positive. Bond forming is exothermic negative. Okay? Okay. Bond energy is the amount of heat energy kilojoules per mole needed to break 1 mole of the specific bond. Now here, look at this. Now you have not done any of this organic chemistry, but never mind. See here, carbon bond to carbon. Okay, now this one carbon to carbon. Okay. So to say carbon to carbon. Now here, shit is called propane. So I'm sorry, but exam come out sometimes like you didn't learn yet, but they give to you. So I must to break all these reagents here. I must break carbon bond. How many carbon bonds? 1 and 2 now. So 2 carbons, 2 carbon bonds. Okay, right? So they give you carbon bond is what? 3, 4, 8. Yeah. So positive, right? Broken up, positive. Okay. So 2 times this is positive 696. Okay. What are the bonds are broken? CH bond. 1 here, 2 here, 3 here, 4 here, 5 and 6 and 7 and 8. So 8 CH bonds now. CH bonds. So CH bond is what? 2, 4, 1, 2. So 8 times 4, 1, 2. Positive, Once you break the bonds in. So it's this one here. Okay. Okay, bonds are broken. CCl. Okay. Only one. CCl, 1 bond in. So CCl bond is 2, 4, 2. Say 2, 4, 2. Positive. Okay. So the total amount of heat is positive by the total amount required 4, 2, 3, 4. Okay, the bonds are formed. Okay, so there's carbon and carbon here. 1 carbon 2. So 2 carbon bonds 2 times. Again, here you can see 3, 4. Minus. Why minus? Bonds are formed. Okay, 3, 4, 8. Secondly, how many H are bond? CH 1, 2, 3, 4, 5, 6, 7. No, 7. Okay, so CH bond, again, right? 7 times minus why bonds are found. This is the value here. What else bond? CCl bond. CCl bond. How many? 1 here. So 1 CL bond here. How much is CCl bond? Here. Port negative. Why is bonds are formulated? 338. Okay, lastly, here also got HCl on bond form. Okay, so HCl bond is 431. So it's negative. So I put all here, right? And I found it is minus 4349. Again, I use a formula. So they ask you for right whether the reaction, that means direction, that means heat or reaction, the overall reaction, okay, equals to bonds broken and bonds formed. So bonds broken is 4, 2, 3, 4. Positive, required energy. Pass. Bonds formed is negative, 4319 is 115 negative. Negative what? Exothermic. Now look at the marking scheme. All right. See? You put all these things here is 1 mark. 4, 2, 3, 4. Check. 4, 2, 3, 4. 1 mark. Check. Bonds formed. Okay. 4349. It should be negative. Now my 4349. Check. 4349. Mark. Next one. Okay. Third mark is minus, minus and endothermic. And endothermic. 1 mark. See? Minus endothermic. 1 mark. 3 marks. Okay? So I finished the whole chapter on energy. So the next one I will do online. I will put this in YouTube. I also put it in your Google Classroom. Okay? I put it under Simon Lyman Chewer, so you can check it out. Okay, I got a lot of videos there for my lower 6 and upper 6. Okay, so this is the first one I'm doing for your class because really no time to cover all these things because I want to finish energy, reversible energy, energy, rate of reaction, reversible reaction, and also redox all within these 2 weeks. So you have to help me by looking at the videos in your free time so that you can do well for your tests. Okay. So I want to stop now. Bye-bye.